We are live. Let's see here. Give it a moment. See if Twitch updates slides. Historic problem. It says we're good to go. All right. So this is CSE598, Advanced Software Exploitation at ASU. Hopefully that's the class you're here for. If not, you are in the wrong room. Now, one of the things I'm curious about is who's taken a Pwn.college course before. I recognize a lot of the faces, okay? Most people in the room. This class runs on Pwn.college. If you're not familiar with that, that's fine. I'll give a kind of a demo of what that means and what that entails. But it is worth opening, particularly for this course. Most Pwn.college courses have some type of disclaimer slide like this. Consider dropping this course. Now, I know a lot of classes say, hey, this is a hard course. This is spooky. I would recommend that you look to your peers who may have gone through a Pwn.college course and ask them maybe after class what their take is. This material moves fast. This material is extremely difficult. This is not an introductory course. This isn't called software exploitation. It's called advanced software exploitation. For this iteration, I have 8 topics planned to cover in 16 weeks, which is actually a pretty light pace. Last time I taught this, I tried to do 14 in 16 weeks. It turns out the fail point was me, not you guys. I was amazed. Students managed to pull it off, but I failed to get things standing up in time, which was kind of amusing. The important thing here is prior Linux system security knowledge is a prerequisite, right? It is an expectation that you know a lot of things. This course is not targeting general CS students. It is targeting students that have a security mindset and have experience where they are very interested in doing low-level exploitation. This is a me thing. I do not curve classes. So there will be no last-minute curve to pass students. You can ask anyone who's taken a class with me before, that is the case. As we go through both class today and next week, if you do have doubts, please consider changing courses or talking to me outside of class. To give you an idea of the type of things that we expect on day one, because as a graduate level course, I can't say you have to take this, right? Every university teaches a different number of things. Here's a list. I'm going to run through several of them, right? I expect that you're proficient with Unix tools and terminal operations, right? You're comfortable in the shell. You're somewhat skilled in reverse engineering. This means you have familiarity with assembly. You know how to use GDB. You know how to use something like IDA, Ghidra, some type of disassembler. So you're comfortable working with binaries where you do not have access to source, or for instance, you do not have access to symbols, right? If a binary is stripped and you're just looking at assembly, you can reason about what's going on at some level. Moving more towards exploitation-oriented things, I expect that you have the ability to write shellcode or write shellcode under, we'll say, common input constraints, right? Not anything particularly crazy, but if you need to write shellcode that has no null bytes, you may not be able to do it right off the cuff, but you know what that ask is and you can do it. Have some ability or knowledge, familiarity with the Linux kernel, at least kernel modules. You have some idea of what exploitation in a kernel context means. Familiarity with race conditions and how to exploit them, so identify them and exploit them. When it comes to memory corruption, we are going to already assume that you know what a buffer overflow is, what return-oriented programming is, what pointer corruption or memory corruption, kind of the implications of corrupting a pointer is. Someone asked me outside of class, what languages are we going to use in this class? The general assumption is that you're comfortable with computer science as a whole, and so you can abstract or adapt pretty easily. As far as what we're going to use in the course, it's going to be Python, PwnTool, the PwnTools module of Python, if you are interested in what we're going to be working with there. A lot of C, possibly some other languages, but that would kind of be a special case, right? If you know Python and C, you're probably in pretty good shape. Have some idea of security mechanisms that exist in binaries, like the NX bit, or non-executable. So like what it needs to have a non-executable stack, what a stack canary is, what PIE is, and relrun. And then just some experience with the glibc heap. You don't necessarily have to know how to exploit it, but just some idea of what it is and how it may work. Any questions about these bullets? Historically, this is a big spooky slide where I get all mean. It is what it is, guys. The plan for the course. Like I said, everything's going to run about 2 weeks. This is the planned schedule for the entire course. Starting today, we're going to be working on a module that focuses or introduces the concept of exploitation primitives. Now, the reason that we are starting off here with this exploitation primitives module is because when I look at this list of things, I'm not going to say all of them are there, but a good amount of them are. A good amount of these skills are required in order to complete this first module. The idea of an exploitation primitive we'll discuss a little bit later. And then we're going to discuss these different kind of machines or subsystems and how they can be framed in terms of exploitation primitives. So how can we build primitives out of format strings? How can we build primitives out of file structs? How can we build primitives out of the heap? And then before we go into spring break, we're going to have some fun here with a module that kind of explores how persistence and botnets work, kind of multi-host exploitation. When we come back from spring break, we're going to do what will probably be the easiest thing in this whole course, which is an introduction to Windows binaries. That's only going to run for about a week. Then we're going to do some Windows exploitation, so some more fancy stuff. We'll do some kernel exploitation. This will be primarily in Linux. And then there's this unannounced thing that we'll do at the end. It is worth noting that finals week is 5.5 to 5.10. The planned schedule does run through 5.12. The question is, like, how do you do that? You know, there's finals week. The day that I have to submit grades is 5.12. This should probably say 5.11. So I have a day to pull grades and upload them to ASU. But the course will run straight through from right now until grades are uploaded to ASU. One thing that's worth noting about these dates is they do overlap. So aside from right now, which is a little bit weird, the general cadence here is modules launch on a Friday. They are due at midnight the Tuesday before class. This sounds a little weird, and people who have taken a class with me, do you like that cadence? Like, that makes sense and it works? Okay, maybe some people don't like it, but that's what we're doing. So that is the plan, and I'm going to try very hard to stick to it. You expected the syllabus list to be longer? Yeah, you know, I'm not going to bite off more than I can chew this semester, Twitch. Right? This I feel I can reasonably deliver. I said that this first module is a little bit short. If I remember right, this is 13 days. Most modules run for 19 days, except for the 3 that I've outlined here, which is the primitives, format string attacks, and then intro to Windows binaries. So the general structure is that this is a flipped classroom. That's why modules launch on a Friday before class. Now, I can't do that now because today's the first day of class, which is why the first module is always weird. A module consists of several pre-recorded lecture videos and a series of increasing difficulty challenge binaries to exploit. On average, it's about 30. Some modules will be less, some modules will be more. The first module is live right now, assuming I didn't make a typo. The way this class works, if it works well, is you watch these videos before class, right? They come out on Friday. That gives you Friday, Saturday, Sunday, Monday, Tuesday to check them out, watch some of it, see what makes sense, learn a little bit about the concept. Starting the challenges before class. So somewhere again between that Friday and the following class, give them a try. You're going to get stuck on something, right? It could be because the lecture video isn't any good. It could be because the challenge is just tricky. It could be that there's just something that you don't know, you're making a typo, whatever, right? But come to class with questions. What I prefer to use class time for is answering questions, doing live demos, interacting with you. If you drive the discussion, it makes it easier for me to make sure that you learn what you want to learn, right? What we're all trying to explore. We do have a Discord where you can ask questions outside of class. It helps me a lot in preparing for class if you ask questions on this Discord, because then I have an idea of what people are stuck on, what people are thinking. It helps me decide what I want to demo. Course grading. There are no exams in this course. The course grade is entirely calculated based upon the average of these challenge modules. Real-time grading is available on Pwn.college, which is the website that this entire course is going to run, which we'll take a look at after the slide deck. Module grades are weighted as shown here. 80% of the module grade is just what do you complete. So if there's 20 challenges, you solve, I don't know, let's do 18 of them. You get a 90% in that component of the module grade. The second component of the module grade is something that's called the early bird checkpoint. This is, in my eyes, kind of a free 20%. The early bird checkpoint exists to encourage students to start early. The number one way that students struggle in this class or in these courses is by starting late, because the modules increase in difficulty. And so students may look at the first one or two or first couple and think, hey, this is pretty easy. By the time you get to the last challenge, these will be pretty time-consuming tasks. And when students misestimate that, you're not able to bang everything out in the last 6 hours before a due date. And so this is hopefully an incentive to prevent that. The early bird checkpoint is complete half the challenges in the first 10 days. If a module runs shorter than what was outlined, so these highlighted ones, then the early bird checkpoint is whenever the due date is. All right. But for any of the modules that run 2 weeks, it's get half of the challenges done in the first 10 days. That gives you 2 weekends, if I remember right, because we're launching things on Friday. Most modules are live for 19 days. Any challenge in this entire course can be solved at any point for 50% extra credit. So this is a challenging course, but I do offer a large amount of extra credit. I believe extra credit is a critical component for these courses. In general, I offer somewhere between 13 and 15% extra credit every class that I've taught. Right here is 13% out the gate. So you can earn up to 8% extra credit for posting memes on our Discord. Our Discord has a memes channel. You can post one meme per week. And if it is a good meme, which just means someone who is at the instructor level at Pwn.college, if they find it humorous, they'll give you a little like, they'll give you a little emoji reaction. If you get that emoji, you get 0.5% of the course grade as extra credit. So how do you post a meme that the instructors like? All we're looking for is something about the content, right? It could be, I got tripped up on this particular sub-problem inside of the challenge. It could be something that you found was amusing or interesting about the material. We're looking for something about the material, not just, oh my God, everything is so hard. For this course, I'm going to be a bit more strict as far as what's an acceptable meme, looking for things that are content relevant. With that said, I'm going to try and be pretty liberal with liking memes. I want you to get the extra credit. All right. Like I said, the tail end of these challenges tend to be quite hard. The reason that so much extra credit is offered is so that a student who is moving through the material and not able to solve 100% all of the modules, you can still walk out of here with an A. You can still do well in the course. You can also earn an additional 5% extra credit by just asking good questions, being helpful, participating on the Discord. We have a thanks system where if somebody answers, you ask a question, somebody provides something that you found useful, you can give them a little thumbs up, a little thanks of reaction. That tallies up. It's on a logarithmic scale, capping at 5%. It's logarithmic, so the earlier helps are worth more. Somebody did the math last semester. 1.3%, I think, for the first 2 thanks. And then it decreases from there. But you can get up to 13% extra credit. So what does that kind of mean? Well, if you did 49% of all 8 modules that are planned, you would get a 39.2% E. That's because you're not getting that early bird credit. Now, if you did 50% of every module and you did it by that checkpoint date, suddenly you have a 60% in the course. And what you're seeing here, despite the fact that that's only a 1% difference in what you solved, is that early bird checkpoint drastically swinging your grade. Right? So doing that extra 1 challenge for every module by the checkpoint is about a 20% swing in the course. Now, if you did 50% of all of the modules that are listed, and you did 15% extra credit or 13% extra credit, then you'd have a 73% C, you'd pass this course. So as far as what is the minimal amount of hard work that's needed, it's 50% of every module by the checkpoint, and then spend some time on the Discord saying things, posting memes. You can walk out of here with a C. I think that's a pretty reasonable bar. Now, this is something you have to decide that you're going to do right now, because memes are per week. It's 1 meme per week. A week will run. We had some questions about this last iteration. Sunday through Monday. All right. That means there are roughly 17.5 meme weeks. I'm still going to cap this at 8%. Just so we're all on the same page. But it means you need to start doing these memes and posting these memes early because you are planning on capitalizing on this extra credit. I would encourage everyone to capitalize on this extra credit because the hardest stuff is at the end of the course. And that means when it takes you by surprise and you have other classes, that extra credit can save you. All right. Now, if you did 75% of every module by completing 50% of it by the checkpoint, you got the 13% extra credit. You can walk out of here with an A. To get an A+, the minimum completion is 84%, completing 50% of each module by the checkpoint, and then you can eke out the extra 13% with extra credit. So that gives you an idea of how much work is required and strategies that you might want to employ to get the grade that you want. Any questions about this? Okay. So, the TLDR. Watch the lecture videos when they're released. Start early. Ask questions to confirm your understanding here in class. Participate in the course, right? This extra credit adds up. Meme early, meme often. Bank it now, spend it later. I mentioned before I started the stream, but we'll throw it on the stream as well. These lectures are live streamed and available online. There are a number of students who emailed me and for whatever reason couldn't show up here on day 1. Perfectly fine. Attendance is optional. This is streamed at twitch.tv/Pwn.college. The streams will also be uploaded periodically to youtube.com/Pwn.college. I don't care where you watch the material. I try and just make it available for you either way. Attendance is encouraged and appreciated. It is actually you guys that make teaching fun. When you ask questions or get me thinking about something in a way I haven't thought about it before, that is a big part of why I go up here and act a fool. Prior iterations of some of the content I listed is available right now on the Pwn.college website. There are no guarantees that that is the content that will be used in this course. You're welcome to try and tackle it, but nothing is officially assigned until it is listed in the CSE598 dojo and assigned to you. Instructor office hours. So this is me. I'm Robert Wassinger. On the Discord, I'm Rob Waz. I haven't decided when my office hours are going to be. I'm going to leave that up to you because it makes the most sense to optimize for when you are available, right? And so if somebody has a preferred date or time, let me know, and we'll figure it out from there. I'll reserve a room, see what we can do. Adam Dupay is also assisting in this course. I'm unsure what he's going to do with office hours. I spoke with him, and he said he might be doing something on Discord, right? As far as being able to access him. So this class is scheduled from 4:30 to 7:30 p.m. That is a long time. I do not intend on talking nonstop for 3 hours. I will if you want me to, but I'm going to get pretty hoarse at the end. My rough plan here is for the 3-hour window to be split into 2 components. The first half is going to be live streamed and is what's going to be on Twitch. It's going to consist of a series of slides. It's not literally an hour of slides. It's hopefully going to be like 5 slides or less. And then that's going to lead into some live demos that apply to whatever it is that we are discussing. Somewhere around the hour mark, when it makes sense, we'll take a 5-minute break. We'll mute the camera. Everyone can have a bio break, whatever they need. And then we'll come back and carry on for roughly another hour. It may be 45 minutes. It may be an hour and 15. They're live demos, right? Sometimes things go fast. Sometimes you go down the rabbit hole. That's part of the fun of having this time. By the time we hit about that 2-hour mark, I'm going to end the stream, and then I'm going to use that last hour here to help you on whatever you are stuck on. So if you have taken a class with me last semester and you attended my office hours, I'm going to do something very similar to that, where it's, I'm stuck on this, let's take a look at it, let's poke at it, let's do some hands-on stuff, right? Unfortunately, I can't do that on stream because it spoils challenges. And that's why the question of when do office hours make sense for me to hold them separately is up to you based upon your schedule, right? Because I'm going to be doing something similar to what I do in office hours with this remaining time. And if nobody has questions and hangs out, that's perfectly fine too. We're just done early, right? But we're going to use that time for hands-on questions. Okay, so that is the slide deck. Everything else is live demos. The way that I tend to do class, as I kind of alluded to there, you get about 5 slides, hopefully with some good memes that you have made for extra credit. And then the entire class consists of me doing real things. Most of what you're going to see is going to be a terminal. This is why when we talk about the prerequisites, being familiar with the Linux terminal and kind of comfortable working in this environment is important. Most of class is going to be something like this, where I'm going to be running something over here, and I'm going to be, I have a do to, dim do 3. I'm going to be writing code over on the other side. And we're going to be running through and iterating on this. All right, so for those that have not done Pwn.college recently or at all, we'll take a quick look at that. So if you, on a web browser, just go to Pwn.college, you'll hit this website. This is the website where everything on this course is going to be ran. Pwn.college is a pretty cool website because it allows you to drop into an environment that has all the tools you may need to start learning about hacking. Now, you do need to create an account up here. So we'll start off by hitting register. We just need a username, email, and a password. We aren't going to spam you. It's just so that we can reset your password. You do not need to use your ASU email. If you do, you get like a cool little ASU fork icon next to your name. But other than that, it doesn't matter. Once you're logged in here, you'll see all of this content. This is all free and open stuff that or educational material that we offer on the site. Now, getting started is how to use the platform and teaches like the beginning of assembly, kind of thinking about how computers work. It's targeting a pretty introductory audience. The core material here, the series of belts, this is kind of the crux of what we try and teach here. These belts do not specifically align with the ASU courses, but to give you an idea of how they're related, the orange belt is roughly CSE598, which is an intro required class here at ASU for all CS students. Gives broad sampling of cybersecurity. The yellow and green belts, program security and system security, that starts kind of going deeper into binary exploitation. This loosely follows CSE466, which is a 400 level class at the tail end of an undergraduate career trajectory here at ASU. This class loosely follows the blue belt, which is the most advanced material, most of the advanced material we have on the site. Now, if you are taking this course, do not click the blue belt. I know what I just said, but the key there was loosely, right? That was doing quite a bit of lifting. And that's what I mean when I say that these topics that I mentioned on the slide deck exist on the website, right? These topics have been explored in previous iterations at ASU, and so we leave the prior iterations of content on there. If you're at ASU and taking this course for credit, you want to go down to the courses, and I didn't add it there. Dang. Well, it will be under the courses, at which point you can click CSE598 Spring 2025. I'll fix that right after class. Now, you will not see all of these. You'll just see this exploitation primitives module. And you want to follow this section. All right, whatever you see in here. Now, an important thing to do, and people always forget to do this, is click on course. I don't care if you've taken a Pwn.college course before, 365. I don't care if you've taken a course in CSE466 with me. You will need to click course under CSE598. You have the syllabus listed here. It's the same syllabus that was linked to on the course catalog. On the left-hand side here, there is identity. Give that a click. Please put in your ASU ID. This is how I know you're a student. This is how I'm able to synchronize things and get your grade. Inevitably, at the end of the semester, people always forget to do this, and then it becomes a problem trying to figure out who is who. On the topic of grades, one of the nice things about this platform is you get real-time grading. Right now, I have an E in this course. But every module, every due date, every checkpoint is all listed here. And every time that you solve anything, this updates in real time. Is that a question?
Yeah. Checkpoints is the third. Is that going to change? I'm assuming.
What did I do? Checkpoint.
It's 6.
Says 28.
No, I'm aware of the time. The progress, it's 6 instead of 10. It's not.
Oh. Good call.
I remember in the syllabus it said third. I just thought you'd change.
Oh, now whatever the syllabus says is what we'll go with. All right. Let's see what we actually put here. It does say first, third. Good call.
So we're sticking with
Well, I'll
that.
stick with the third, man. Right?
Thank
That's fair. Last semester I did half. Yeah. All right. Yeah, we'll go with third. Just know that it's there to help you. Please do not procrastinate. So yeah, if it says a third, we'll go with a third. In general, for things like that, I try and be reasonable. So if you catch me, you can hold me to it. Okay. So why do we use this site? Well, when I go into a module, I said that a module consists of a series of videos here. I think this is the last one that you get that's young. If you've taken Pwn.college courses before, I think everything after this module, you get me. So there's a series of videos here where we have like the introduction. He'll talk about these concepts. And you can watch them here. You can watch them on YouTube. The slides are embedded right here below. And then we have some challenges. To kind of solve challenges on the website, we start off by clicking either Start or Practice. I'm a big believer in hitting Practice. And now it says the challenge is successfully started. We can interact with it through either VS Code or a GUI desktop. So if we look up here at the top, we have Workspace and Desktop. If I click Workspace, what we'll get in our browser is a VS Code environment. So if you like working with VS Code, this provides you a nice interface to work with things. I personally have no idea how to use VS Code. The only thing that I've almost managed to remember is how to make a terminal appear. I think it's like Command tilde, but I'm not entirely sure about that. So if I run inside this terminal inside of VS Code, we see I have this challenge. I can use VS Code to, for instance, create a file and work in here if this is how I prefer to work. Now, for some of these tasks, going back to the expectations, I said you have some familiarity with like Ghidra, IDA, some type of decompiler. Well, we also provide, via that desktop link, access to a full desktop environment that is running inside of your same instance. And so if you prefer a full desktop, and for some things you do need a full desktop, I can now use a graphical tool, for instance, like IDA. And we can open up that challenge binary here in IDA and look at what's going on here. The way that the challenge environments are set up is the challenge is always located in /challenge. Your home directory, which is home hacker, is where all of your files are located. Anything that you store in home hacker will persist across challenges that you start. But the task for every single one of these is to obtain the contents of a file that is located at /flag. Now you'll notice that /flag is owned by root, and we are the hacker user. This is the fundamental problem that every challenge asks you to solve. Now the means by which you can do this is the file that is located in the challenge folder. And so here we have a binary that is named baby prime level 1.0. We see that it is owned by root, and it has the setuid bit set. So if I were to run this, it would run as root. And so this is my means of privilege escalation. Once I exploit this binary, I'll be able to output the contents of the flag file. And I'll get something that looks like this. This is a flag. Pwn.college, a curly brace, some text, followed by another curly brace. Now, since I started in practice mode, this isn't a real flag. The real flag will consist of randomized letters, numbers, symbols in this curly brace. We can take that value. We go here to where we started that challenge. We paste the flag. We hit submit. In the event that the flag was correct, we get a nice success message. In the event that it's not, we'll get some kind of error message. Practice is not a valid flag. The third way that you can interact with this platform is via SSH. If you go to the little gears in the upper right, you can hit SSH. If you paste in your SSH key, you can then do what I did here, where I SSH hacker at Pwn.college. And this gives me an SSH connection into that same environment. I have all of my files here in the home directory, and the challenge binary is still located there. Anyone have any questions about the platform or the website? No? Cool. All right, so there was a nice long list of prereq content. I actually have 2 classes to talk about this module. And so I'm totally okay burning time today on any questions that you have about any of these topics if you're not familiar. If there's not anything that you specifically want to ask, that's totally fine. What I'll do is we will delve into the first challenge, which utilizes most of these concepts. I try in general to not solve challenges on stream. I'll make a rough exception for this one. So if it falls out, it falls out. But I want you guys to be kind of driving the conversation. Tell me what you're thinking when I present a problem, and that will guide where I go or what I do to try and get to the flag. All right. To start off, something you may want to do, and I would suggest it, when you're encountering a binary and you don't know what it does, run it. Okay. This is what we get. Well, what should we do? Okay. The challenge says, the challenge is listening for a connection on TCP port 1337. The challenge supports unlimited parallel connections, and it says storing the secret in the BSS. What do you want to know?
Can we talk?
Okay, how can I talk to it? What's one way that we can talk to it? Nice, easy way, netcat. So I can run netcat localhost 1337. I get the message over here. Welcome to the message server. It says I can malloc free, scanf, printf, send flag, and quit. Well, you know, this is level 1. It's got to be pretty easy, right? We just run send flag and it's done. Okay, so it asks for the secret. All right, well, any takers on guessing what the secret is? Flag. Okay, this says not authorized. So it turns out it wasn't that easy, right? And this is the type of reasoning that we're going to have to try and go through for all of these challenges. So I could run with something else, right? We could type in some other command. I'm malloc. It says nothing. If I give it free, I get nothing. Printf, I get nothing. All right, so this isn't a very helpful binary, is it? So what tool would we reach for here? So the statements for Twitch here was anger. Somebody said strings. All right, that's interesting. I'll take it. Right, that's good thinking. I don't think it's going to yield anything here. But strings is a command that you can run to get any strings that happen to exist in the binary. So the thought here was maybe the secret value exists statically in the binary, right? Yes, as Twitch identified, which is what I would have responded as well, anger currently does not work on the dojo. Otherwise, we could.
Really?
Yeah, next.
Oh,
Same thing for Binja.
wait, but do you mean just anger management or anger?
Good question. I'm not going to find out.
Just type anger.
No,
It's a CLI.
I know, but
You see, you can use the decompiler CLI.
I've done that. All right, but I don't think that's what we're going to be doing today. Instead, we will reach for a friendly graphical tool. All right, so we have IDA. For those that are unaware, Anger is a CLI tool, but there is a graphical interface that allows you to get something very similar to IDA. These tools are known as decompilers. What they do is they lift assembly that looks like this to something that is a close approximation to C. The problem here is that with decompilers is that it's incomplete information. And so there's lots of stuff that the decompiler can't know. And so a lot of things are just guesses. And so things like variable names, function names, things like that, oftentimes are not recovered. But you know what? On this binary, it's not too bad. So we see here, it prints out that friendly message. It is a socket server we're going to call bind listen. It says it's storing the secret in the BSS. And then it calls this load secret function. Now, somebody on Twitch suggested, hey, we use strings. Looking at this, I can say that strings is probably not going to work. Anyone want to take a guess at what's going on in this function? So we see that it's pulling from random, right? This flag seed, we were to double click on that. We see that this is opening the flag file, which we cannot see. And then it is going to use that as a seed for random values, right? And so it's reading the flag value, which is the secret that we can't know. Based upon that flag value, we're going to seed a random number generator. You know, Justin, maybe you can teach me things in this class.
Not if it's IDA.
Oh,
I don't use anger CLI.
really? You used to be Binza.
I use Binza.
Okay. Like I don't even know like back. I'm a GDB enjoyer. So we saw that this flag seed function is seeding a random number generator based upon this value that we can't know. It's then going to call rand, and it's going to get 8 random bytes, and it's going to place them at some address. The address here is whatever A1 is. And so there's some, this says it's an Int64, but we can reason that it is actually a pointer. There's some address being passed into load secret, and we are looping through and placing random bytes at this memory address. So I think it would be a reasonable assumption, although not always, to trust what the binary says it's doing. And we'll say that, all right, there's 8 secret bytes that are being loaded into the BSS. That means that this pointer here, this address, should be in the BSS. If we double click there, we see that it is a memory location that is in the BSS. So this does make sense as far as what the challenge is telling us and what we see. Somebody says, seed the random with a static value. So if I could edit the binary, I could. And if I could edit the flag, I could change what the randomization is being seeded with. But I don't have the ability to do either of those. If I change the binary, I'll lose that set UID. That set UID bit. I'd have to make a copy of this, and it would lose the set UID bit. So then it wouldn't be accessing the same flag file, right? So unfortunately, I do have to just accept that there's these random bytes that I need to somehow uncover at runtime. All right, going down a little bit further here. If you've taken 466, we've seen this pattern before. What's going on here? All right, we have an infinite loop where the binary is going to call accept on that socket that was created earlier. And then we're going to spin off a thread that's going to call run thread. So on 466, most of what we saw were fork servers. In this case, it's a thread server. So where do I want to look at to carry on what happens in this binary? What function do I want to explore? Run thread. All right. So we'll go into this guy. Is there anything interesting here? Challenge? What's everything else doing?
Messing file descriptors.
All right.
File pointer.
It's messing with file descriptors. So what it's doing here is when we connect to the binary over the network, it's going to duplicate standard in and standard out. So that way those are both pointing to the network. And this binary can just behave as normal. So like printf will go to the socket. And we have to do that within the context of this thread. And then it's also setting buffering on those file descriptors to hopefully make it so that when things get written, they get to us. And when we write things, it gets to the binary. So we go into challenge. This is the meat and potatoes of this thing. And what we see here is that write message. So it lists the commands. We have an infinite loop where it is going to read in a string. Based upon the value of that string, it's going to perform some type of operation. And we can now see why when I typed malloc, nothing happened. When I typed malloc, it was looking for a number. Okay. What is the use of this number? Right? So we scanf %d, and we have v4. Is everyone familiar with scanf? If you're not, how would you find out? Man page, that's right. It's not Pwn.college day one if we don't tell people to read the man page. So this is fscanf. We can type man fscanf, and we get the built-in documentation for how this function works. Now, scanf is a bit more complicated function because it has variadic arguments. So this means it can take a various number of arguments. It could take 2, it could take 3, it could take 4. And so we have kind of this dot syntax. But if we take a look at the description, what we'll see here is that scanf takes, I'm going to say a format string. Yes. It scans input according to the format as described below. Version. Okay, does everyone know what a format string is in like printf? Cool. It's going to take a format string, and then based upon the format arguments, it's going to get passed into the memory locations that are specified there. Since there's one argument specified, there's one location, it's going to read in a number, it's going to put it at this location. How is this location being used? It's accessing, it's an index. So this is an index into an array. So there is some array that is determining whether or not a value is stored. And then there is, if it is not stored, then we're going to apparently copy that index into D2 for whatever reason. That's essentially enough. And then we malloc, and we store that pointer into, it looks like, so I would guess this is an array, but IDA is showing this as a pointer plus some offset, right? I would envision it as an array of pointers, though. Okay, so we can malloc some number of pointers. I can scanf. We see a similar pattern here. I give it a number. It's going to check if it's stored. If it is stored, then we can read in a string of up to 1024 bytes in length. I can free. Again, specify an index. It's then going to call free on that. It's only going to free it if it is stored, so we can't, for instance, double free here. And then we have that send flag function. Send flag prompts us for a secret. It is then going to read in up to 1024 bytes of input. It's going to check if the secret that we provide is correct. If we take a look here at how that is working, it's going to call load secret and then do a string comparison of whatever we provided, which was this A1 argument with A2. A2 is probably getting set here by this load secret. And we see the load secret is doing that same seeding and randomization. And so when we try and guess the secret, it's going to dynamically compute it. So this isn't something where I could, do some memory corruption, like overwrite it with A's, and then, haha, the secret is now A's, right? It's figuring it out after we prompt.
I think escape this back.
Escape? That would be amazing. It would enrich my life. You have done it. You have enriched my life, sir. Okay, so it's then going to compare the two strings. V2 is if this equals 0. It's then going to set. Actually, don't really care about that, do I? It's going to return V2. Hopefully, it's in the return value. So it checks if the secret is correct. Yeah, okay. So we're in this if. So it's going to return whether or not the string matched. If the string does match, then the challenge will write authorized and it will call win. If you have done any number of Pwn.college challenges, you should always check for win functions. Win functions are great, and they do exactly what one would want to win. It says you win, here's your flag. It's then going to open the flag and write it to, I assume, standard out. Yes, it's going to write it to standard out. So these are the rules of the game, kind of what the binary is doing. Anyone have any thoughts on what we need to do? We need to get this secret, right? And the binary gives us, we said malloc and free. So how can we use malloc and free to get that secret value? This is right away where that heap exploitation part, right? Becomes kind of important. That's why we couldn't open with this one in previous iterations, but we can now. So I name everything do.py. You should not. You should name your exploit scripts something a little bit cleaner. So we have the ability to malloc and free, but it's checked, right? We said that it checks if it's stored. And so as a single thread of execution, there's not much I can do, right? Is this a single thread of execution? No, it is not. We said earlier that this is, in fact, a thread server. This is where knowledge of race conditions. Anyone see a race condition in this? So typically when we talk about race conditions, what we're looking for is something called time of check, time of use. And so we're looking for where something is used and where something is checked. This was kind of weird, right? is setting a variable that doesn't need to be set. And so when I scanf to read something, it's checking if something is stored, right? And so if I do malloc1, I can scanf 1, we can give it hello world. I could maybe not.
Oh, is it like a size, another argument to malloc or something?
No, when I look here, malloc has one argument. Let's connect fresh here. Well, malloc1, we will scanf 1, say hello. Oh, yeah.
Just scan it.
Scanf is going to go for white space, right? We'll say hello, and then we will print f1, and we get message hello. So that was my bad there when I had hello space world. The hello space was consumed by the scanf. Scanf is white space delineated. So then I was passing another command of world, which resulted in unrecognized choice. I'm going to get stuff wrong. It's fun that way. So I can do this. Now, if we know a little bit about heap exploitation, we know that we, generally speaking, are trying to target heap metadata. And so one of the things that I may want to try and corrupt is the tcache next pointer. Yeah? Now there's something that I'd have to do in order to like even get that going. And I could keep messing around up here in netcat, but this is going to go into a very big rat's nest if I do. So instead we're going to start writing a Python script to automate this. So user bin n python3 from pwn import star context arch AMD64. All right, we'll say r equals remote. I'm connecting to localhost on 1337. I'm doing the same thing that I did up here with netcat. I'm now just doing it programmatically in Python with pwn tools. Okay. My plan here is I want to corrupt a tcache next pointer. Why is this something that I would want to do? We did this in 466, guys. But what does corrupting a next pointer of the tcache give us?
Malloc next time we control where.
Right, we can control the address that malloc returns. Right. For those that are unfamiliar, I'll throw GDB on this, and we can take a quick look at what I'm talking about here with the heap and tcache. But first, we have to create a scenario where we can look at it. The tcache holds freed pointers, right? Or freed allocations, I guess would be the way to put it. So we can't really look at the tcache until we have some freed allocations. So we're going to create some. I'm going to say r send line. What did I do up here? malloc1. I'll say malloc1, malloc2, malloc3, malloc4. I'm going to just malloc4 things. Maybe. No. My Vim is not as good as I wish. Okay. So we malloc 4 things, we free 4 things, and then I fix that up. We'll import time, and we'll say time sleep for some giant length of time. Just so we can take a look at this. Now we'll make my script executable, give it a run. Helps if I write valid Python. Now let's take a look at this with GDB. We'll look for the challenge process. There it is. I'm in practice mode. Practice mode allows me to use sudo. So this allows me to, for instance, attach a debugger to this challenge binary. In the actual challenge environment, you will not be able to do so, so your exploit does need to run start to finish without access to a debugger. We'll say sudo gdba 2973. Boom, I've attached a debugger. I use a plugin called Jeff that gives me all of this pretty info. And Jeff is going to fail me. Oh, Jeff. All right. Let's see if Pwn.tools will, or not Pwn.tools, Pwn.debug will show what I want.
I think it's just Heap
Was it?
or Heaps.
Heaps. Yeah, I want the equivalent of heap bins. New. Okay. Debuggers will fail us today.
Is it possible that the debuggers are right?
Is it possible the debuggers are right? I suppose that no, that should go to the tcache.
Sure.
So this I believe is like a Dojo anomaly. This also has a custom libc, and I think the combination of those things makes this a bad time. Okay, so if we were to scribble this out and think about what the tcache is, when I call malloc, I get a pointer, right? When I free that pointer, the tcache is a singly linked list of all things of a specific size that have been freed. The way that a tcache chunk is structured is there is a next pointer. And then there's some space. That is what a tcache chunk is. The tcache consists of a pointer to a key tcache chunk, which then points to a key tcache chunk, which then points to a tcache chunk. Right? And this goes on, I believe the max for tcache is, I think, 8. And so this is a singly linked list that can go 8 chunks back. Because this is a singly linked list, when I call malloc, what happens is the most recently freed chunk, so whatever is at the head of this list, gets returned to me when I call malloc as part of the heap implementation. And so what I may want to do, or try and do here, is overwrite one of these pointers, one of these next pointers. But I can't do that in the context of a single thread, because of this stored check. Well, let's think about what happens if I have multiple connections to this thing. Right? Because I can do that. It says it takes unlimited connections. It does take unlimited connections. And all of these threads are referencing the same memory because threads all share a virtual memory space. So in race conditions, when we explored that in earlier Pwn.college material, we had kind of a general strategy of finding whatever it is that we want to mess with or avoid, which in this case is this stored value, right? This is the thing that's given us grief. And we want to flip it really fast. Because if I flip this really fast, there's a chance that it's stored at one point, and then it's not stored in another point, or vice versa.
Other way around.
Is it the other way around?
Because malloc checks if it's not stored.
So but what I'm trying to do is I'm trying to overwrite this next pointer, right? And so I'm trying to get through scanf, because I'm trying to overwrite this when it is a next pointer. And so I want to pass stored. So I need this to not be stored and then be stored.
Yeah.
Okay. So that means I need multiple connections. We're going to have to fix this. We'll have R1, R2. I'm going to do the same thing with R2. All right, so we've got that. Somebody says, is safe linking messing it up yet? We haven't even gotten there yet. All right. This is a great culmination challenge. There was a non-zero chance that this was going to be in the tail end of 466. It didn't end up happening. Say this challenge does have safe linking. It has all of the goodies. All right. So if I need to trigger this race condition, I want to flip this stored back and forth. What do I want to be calling? What functionality in this binary? What set's stored?
I think free.
Okay, free. And then the other thing is malloc. Okay, so we want to flip this stored bit. So I'm going to use OS fork for my racing. I would strongly recommend that you do that and not use Python threads, because Python threads aren't actually parallel. Is that right?
Yeah.
Yes, they're concurrent, but they're not parallel. And so that will work against you. But when I call OS fork, I'm creating a separate process, and that is where I'm going to do my work, which means both processes can run at the same time. So if pid equals 0, so this is my child process. Which one do we want to use? R1. We will send line, malloc1, free 1. Probably want to do this more than once, right? Race conditions always work the first time, don't they? Let's go for what, 1,000? 1,000 seems reasonable. Okay. Now, it's also very important that when you start spawning off children, that you make sure they die. If you don't do that, your code will be a giant mess. And so right here, I'm forking off one child process that is just going to call malloc and free a bunch of times, and then I am exiting. If I don't exit, the child process will continue execution outside of that loop, or outside of that indentation, or that scope, and that will make your code very messy. Okay, so I'm malloc and free. Now, our strategy was to scanf and try and overwrite this thing, but that's going to be a little bit hard to verify, right? Let's just prove that there is a race condition. How can I do that? We'll just verify that we're sane here. I have the ability to malloc, free, scanf, and print. All right, there's only one other thing I haven't used yet, and that's print. So let's do that. In R2, I'm going to send line, what's my command, printf? All right, I do not need to kill this guy here, because this is my parent process, and I want him to continue running. Say R equals R2 receive. We're just going to get a whole bunch of what we printed here. So what we're doing is we'll simultaneously malloc and freeing, which is hopefully flipping the stored value right here. Find, where's our malloc? free. So we see free sets the stored value of whatever index I specified to 0. And then did I scroll past malloc? Malloc sets that stored value to 1. And then I'm simultaneously trying to print it out. And this print check for printf does two things. It will either output none, or it'll output the value. We saw when I malloc scanned f printed, I got my value. And if it is not stored, then we get none. I'm going to print out. We'll split it on new lines. All right. It seems reasonable, right? Maybe. Maybe not. Failure. Bam. Easy, just a paren. Did I get anything? I did not. I kind of expected something.
Shouldn't it be receive and the number of bytes?
You can. So I could specify give me 1,000 bytes. But I'm just getting this right here. I'm just getting message none. Right? Like it is doing what I'm asking. Send line and F. That should go. Free balance. Because at a minimum here, I should be calling print F1 1,000 times, and so it should be saying something a bunch of times.
Well, you're only grabbing the end, right?
What am I grabbing?
The out is outside the for loop, so you just grab.
Yeah, but that should, I mean, we put it in there. That should all sit in the buffer of this thing. Interesting.
Wait, did you not? There was a leak, I think.
There-
Some bytes like when you did that. So
See how far I can go. Oh, okay. So we're now getting some garbage, all right? And Justin here called this thing a leak. What did I print?
something.
I printed something, right? And I got something that isn't none. We may be able to make a little bit of sense of this thing. That bothers me that I'm not getting it down there and out. It should be there.
To do like I don't know. Usually I do like receive all with a timeout rather than receive. I don't.
Oh, you want
receive
okay?
to do-
All right. Is this the move? Okay. Yeah. Sometimes I dry run things. Receive worked like 2 hours ago. I'll take it. Best practice. Use receive all. Okay. So we get this giant mess of nonsense. We probably want to be a little bit smarter there. So let's split this thing on new lines. out, split, new lines. Cool. And then we will set out is going to equal L for L in out if message not in L. That should remove all, oh, not message. I want none. If none, that would give me nothing. If none is not in L. So that should filter out all of those message nones. I'm then going to print out, let's just print out. Let's not get too fancy. See if we get what we think. All right, so we've got a whole bunch of the cases where it leaked. Good stuff. I probably only need one of them. Let's make sure that this is a leak. Good thing we checked. We'll filter this again, do the same thing, except this time we will say that I for sure want message in there. Okay, so I'm able to, looks like so pretty consistently here, get this leaked value. Now this is just a whole bunch of garbage bytes as far as we're concerned, but we can make this look like an address. We can P64 it after we pad it to 8 bytes with null bytes. Wait, P64? No, U64. And then I'm going to, well, I'm getting quite fancy. Let's okay, come on, Vim. We'll say leak adder equals this. So I'm just taking those bytes and padding it to a length of 8. I'm converting it to a number. And now we'll print out the hex representation of this address. If I get my parens right. What did I do?
It's a strip. It has message colon at the start of it.
Aha. So Justin correctly identified that this thing has message colon space, followed by the actual thing I'm interested in. So how do you want to get rid of that, Justin?
You do dot replace.
Ooh. A bold choice.
The other option is split, but
Yeah, I would have split. So we'll take message and we will replace it with nothing. This object has no, oh, out 0.
oh yeah.
Naming things is hard. All right. So we're able to get this value. Did we win? No, we didn't. Can we make sense of this value? Well, let's see if this actually means anything. Okay, so I ran VM map, which if you're not familiar, gives us a list of the virtual memory addresses inside the process. And if I provided an argument, it should show me the region of memory where that address exists. So for instance, if I were to grab this address here, hopefully Pwn.debug behaves the same way as Jeff. It does. If I give it an address and it's a valid memory address, it'll show me the region of memory where it is located. And so when I do that with my leak, it says you have a whole bunch of garbage. It says, hey, this isn't here. Well, as Twitch mentioned, this binary uses safe linking. That's right. We're starting off strong. Does anyone remember what safe linking is on the heap?
Mangle the next pointer.
I'm sorry. Okay, so it mangles the next point. Right? So what I got, my garbage value here, is a mangled next point. It's not a next point. Can I unmangle it?
Yes.
Okay? I don't expect you to know the exact thing, but at a high level, what do I got to do this bad boy?
So, yeah.
There's some XORs. It's like a crypto thing. Yeah, all right. I agree, right? I feel the same way about it. So the poor man's unmangle function, all right, it relies on a particular property between the position and the pointer, which is true for what we are doing. This relies on the position and pointer being on the same page, what I'm about to do. If the position and pointer values are on different pages, then this won't work, right? And you have to do some more complicated math. But if we assume that the position and pointer are on the same page, then we can make some assumptions about, I don't want to get this wrong. Okay, where's my dry run? Bam. When in doubt, demangle, yoink. Boop. I would have gotten this. I think I would have got that. All right. But what you're doing is you're bit shifting the pointer by 12. That's going to get you to the page. Because if the position and the pointer are on the same page, then the value of the position and the value of the pointer bit shifted by 12 are going to be the same. You're taking advantage of that fact. This actually gives you access to an intermediate value, which you can then XOR out of it. If you want to see the full math on that, I have this great like 3-page write-up of doing all of this math by hand, or you can just look at this function and be like, I'm good with that. All right. This is our magic anti-safe linking function. Twitch, I saw all of your comments, but it was just too late. I appreciate it though. You think strip is less? Oh, L strip. Strip is less verbose. Is L strip a thing?
What else strip is?
Now I want to know.
Strips everything.
Okay, so there. Well, I'd have to do like. Copy the string.
Leaving white space. It's not leaving the white space, right?
Yeah, but I assume if chars is if chars is not none, remove the characters instead.
Okay. So you can give it L strip and then the message string.
Yeah. Okay. It's good to know it exists. I'm a bit stubborn in my ways though. Okay. Where was I? So I had this. Where'd my demangle go? This magic demangle function. If we trust the magic demangle, I should be able to demangle this address, which should give me a heap leak. Because remember, this thing that we're leaking is a mangled heap pointer that is the next pointer of a chunk that is freed on the tcache. Let's see if that gives me a number. It does not. Leak bytes equals out replace. Oh, we just didn't get anything. We lost the race. Oh, that's because I'm over here in GDB. Okay, so now I have a different magic value. And this magic value does correspond to memory. So we did good. We now managed to leak a heap pointer. So we know our race is valid. Now our greater goal here. Oh, I said you guys get a break. You want a break? We should break. All right. When we return, we will somehow go from this heap leak to the secret value in the DSS. I think we can do that. But for right now, let's take 5 and give it a minute. All right, we return. And right now we have this heap leak. Okay. So I showed that I could leak this. And this was meant to be a proof that this race exists, which it does. But this value is also actually needed. Because if I can leak this value in a race, I have the ability to write via scanf, so I could overwrite this next pointer, right? But I can't just write the raw value that I want, right? Because of safe linking. So I actually need this heap address anyways in order to safe link the pointer that I need to write. So this wasn't a waste of time, thinking about what was going on here. So I have this heap link. Next question is, well, where is the secret? Well, I failed to do one of the critical steps when you first look at a binary. My approach is, just run it. Right? But there's something else you might want to do. Check sec. So check sec gives us some information about what protections exist, and we see right here that PIE, this binary is not compiled with PIE. That means that addresses in the binary are going to be known before we run it. Right? It's not being randomized by ASLR. So, where's the secret?
I think it was 40 something.
It was 40 something. You gotta send a flag, secret correct. Load secret A1, whatever. It was up here, wasn't it? Main, load secret. Okay, we saw that it was giving the address where we're going to put the secret as the argument, so it's this thing right here. So it is at 4054C0. Up here near the top, our target address was 4054C0. And just to see if that's correct, we should be able to, in GDB here, examine the string. Is that right? Now that's going to dereference it, isn't it? Examine the giant hex at 4040. No. Let's do it right.
I think it's 50.
54.
Or examines S, but actually.
Can you examine S?
Yeah, you can.
Oh, that's gold. That's gold right there. So there our secret value. These are the 8 bytes that were randomly read in here. If we weren't in practice mode, I couldn't grab that, right? But we do see that we have the correct address. All right. So what do I want to do now? I want to overwrite the next pointer with a mangled target address. Oh, we need to have a mangle function. Oh no. This one I think I know. You take the position, you bit shift it by 12, and you XOR it by the pointer. You trust me? You can say no. It's totally valid to be like, I don't know, man. Look, it is.
You don't return it.
All right, you probably do want to return that value. So my mangled target address is going to be a mangle of the heap leak address with my, what did I call this? Target address. And that is what I want to write. Okay. Now I can do the same thing that I did up above here, where I'm flipping the stored bit, but instead of calling printf, I'm going to call scanf, right? And try and overwrite that next pointer. So let's just yoink that. We're still going to be malloc and freeing. This time we're going to scanf into 1. I'll make that a byte string so that I can add the P64 of the mangled target address, right? We'll pack that to 64 bits and append that on there. And I probably want a space after my 1 so that scanf will parse this stuff correctly. Okay. If I'm successful, how do I know? Or like, how do I know I'm successful? I can do this, but then what?
You print F1.
if I print F1, what do I get? I would either get the value that I put there, or I would get none. Is that what I want to do? I mean, I could, but what I'm really more interested in is mallocing one more time, and hopefully I get to malloc the thing that I put there, right? Malloc into 2. And just for sanity's sake here, let's do a clean of everything in case there's any, which I'm sure there is, garbage chilling there in the buffer. So we'll send malloc2. We'll send printf2. Why use the same quotes when you can change them up? And then we'll print R2. We're a fan of receive all with a timeout. All right. If I wrote this correctly and we're thinking about it right, we should not have that happen. What did I do? Sandra EOF. Why did I close? So it's closing the connection and it's doing it on line 85. It's grumpy here. Might be grumpy there. Too clean. When in doubt, just run it again.
The crashing.
I think I'm sure the game.
Do you see it? We open, Pwn.college yells at me about bytes. I don't care. Receive all. Is this receive all that's getting me? Does receive all close? Are you sure? Okay. And it's grumpy at R2? R2 7. Yeah, it's not mad at me for the clean. Well, let's just not do that. See if we explode. All right, we still explode.
Fork a second time.
I do not fork a second time. Good call. Yes. All right. Okay. Well, you fixed something. So we clean, we fork again. Pids OS fork, that's the child, that goes there. We're good until here. Did I import time or sleep? Neither.
Possibly.
I just didn't do it up at the top because I'm a savage. We get to there without blowing up. Yes.
One of the connections closed by that point. Is that right? It says something.
Okay. It closes both. So is it this? Is it the sys exit?
I think that's like calling the garbage collector or something.
Yeah. Let's go with that. Give it 3 seconds. Let's still close.
Great connections. That's awesome.
Because it's showing it from the child process, right? But it's still going to standard out.
Wait. So then at closing is right because it's just a that doesn't make sense.
No, but it should. Let's do this. Because I didn't do it up top. Let's just keep the child alive. And let's not debug. I'm a believer. Why? It's the beauty of live demos.
I'm a liar. It closes at 2.
Receive all?
Yeah.
You got me with receive all?
Yeah.
Gosh dang it, Justin.
I was gonna just use receive with timeout, can't you? Or, I don't know.
Okay. All right. I feel a little bit better now.
I swear I'd use it like that, but maybe like.
Okay. So let's do receive then. And just give it some big number there. Because that should go until EOF. And then, or not E, yeah, which it will hit when the program is done passing output. So that won't infinitely block. Run a challenge, run a script.
Oh, I think it is your sleep.
That sleeps in the child. Oh, you think it's hitting my go to sleep? That one there. Okay. You get a message. We get this. We mount. We print F. We print this. The only issue I have here. So I've been doing everything else on R1. Let's stick with R1. Oh, we did get something interesting there. Did you see the binary yelled at me? What did he yell at? We tried to free an invalid pointer. So we're getting there. What are you mad at me for now? My Mac's gonna die. It's all over. We're close though. All right, we have power. So our problem right now is receive versus receive all this nonsense. Are we getting enough bytes to actually parse or not? Hmm. So we could just be, okay. Storing the secret in VSS, free invalid pointer. And so we're doing something, but we're blowing up sometimes here. So what could I be doing wrong here? Mangle target address is mangle heap leak, which should be a demangled target address. It's R1. That's R2. That's R1. That's R2. I'm a silly goose. Does anyone know what the T in tcache stands for?
Right.
Thread.
Oh,
You know what happens when we can make two different connections? We make two different threads. It's important. And the threads actually have their own heaps, their own thread local heaps. And so what I was doing there, just one of the reasons this was becoming problematic is I was using scanf in R2, but I was printing something from R1, vice versa. So I kind of created that problem myself here because I'm malloking things from up here. I'm malloking them from thread 1's heap and then freeing them into thread 1's tcache. Here I'm malloking things from thread 2's heap and putting them in thread 2's tcache. And so I need to pay attention to that. One way to make that a little bit less of a problem is just make sure that all of your allocations are coming from the same heap, because you can actually malloc from thread 1's heap and then free that address into thread 2's tcache. I get this message. Did I just write like the world's longest loop here? Hello from here. I would love to throw IPython on here, but it turns out if you call OS fork, IPython is very not happy. Okay, we get hello from here. I get, oh, I am getting something. Okay, so this is the value from printf, but it is definitely not those characters. Things are working, but they're not working. Can we make sense of whatever this is? Let's call my Python session. It's P64, whatever this is. New line that I don't care about. That will be good, right? Must be full character. Must be. What are you grumping about? Oh, I want.
Shouldn't it be bytes? Yeah. Yeah.
Oh, okay. My brain's falling out. Okay. So that is what I'm leaking. Let's yoink my demangle. Demanjo. Whatever this is. I bet what's happening is that we're just getting the wrong chunk. And this is a valid address, which it is. So it's fine. We could just be losing the race. What was my nonsense? Because my nonsense here looks like my nonsense here, right? My leak. So I'm probably just losing the race here and not writing it. And so what I'm leaking down here, what I'm printing, is just a valid heap, mangled heap. What can I do to improve my odds of winning this race? More, what'd you say? More for loops. So I could do more for loops, but there's like fundamentally a problem here of just the slowness of sending this with every loop. I can be a little bit more efficient by blasting out a giant string that is all of this.
I'm showing out of space at the end.
So this is using send line, so there's going to implicitly, oh no, you're right. Right there is not.
Well, not just there, but in the message itself.
Oh, yeah.
Just 'cause-
So I want message to have the null byte there, so then when I multiply them and append them, it's between all of them. You agree? Okay, good catch. So that's going to blast out scanf1, blah, 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 scanf1, blah, 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 a whole lot more, because every time that I write out to the network, the program will hopefully be doing this as fast as it can. It doesn't have to read back from the network or wait on the Python side to get it. All right, so we're not getting what we want, but it doesn't mean that we're wrong here. Other comment from Twitch here, you should use clean or timeout equals 3 with receive. Well, right now my whole thing's hung because I still have GDB hanging out over here. Let's get GDB off of it. Find receive. You say you can just timeout equals 3 for receive. That is beautiful. So this could just be doing that giant loop. Okay, I got my hello from here. I didn't get anything interesting down below. Okay. You're close.
I don't think that'll work.
Are you sure there, Twitch? Did you trick me here with the timeout?
We have both like the number of bytes and the time.
10,000 seems like a reasonable number. This is just the fun of race conditions. But you can see what we're doing even if I don't hit it, all right? Empty string. Every one of these challenges is based off of this concept here, right? You're creating some type of a primitive to read or write from somewhere in memory. Now, my code that I wrote here should not be replicated, right? This is a giant garbage, just garbage in, garbage out, write stuff from start to finish. And I did that on purpose because the idea of having an exploitation primitive means that you have something that just gives you a code that just gives you the ability to arbitrarily read some memory address, right? I have almost something that I definitely have something that reads memory address that I can specify. But I don't have something that writes, right? But you could imagine that we package this up into functions that are defined. Now, one of the other things that can cause this to fail is there are bad bytes, right? What do we know about memory addresses? They can be randomized with ASLR. Is there anything that stops ASLR from having a space in it? No. There's nothing that could stop it from having a space, a tab, white space, anything that interacts with how I'm parsing this, how this is printing, and how we pass things in, right? When I mangle an address and I try and write it in, what happens if there's a new line in what I'm writing? It breaks the entire chain, right? This is a very real problem in this module. And what you'll need to do is write code that deals with it so that you generate arbitrary read and arbitrary write primitives that automatically retry or detect fail cases early to try and get your way through this. If you trust me that we can get this value to hit, we can call it there. Do you trust me? You want to hit it? You want to hit it. All right. So let's see. What else can I do to make this run faster? Well, I could apply the same strategy here. Put a space on the end. Do 1,000 there. Let's see if that gets me there. Yeah, this receive is quite unreliable. The empty string. This is R2.
Could it be that we might be winning the race in one of them, but the last one isn't the one race, since we're going through all of them, right?
Since we're going
Because
through,
we're writing the mangled address repeatedly.
we're writing the mangled address repeatedly, but we are malloc and freeing this top chunk, right? This top 3 to allocation on the tcache. And so the things that could occur here in this race is we get like unauthorized, right? We could partial write. No, could we? I don't think we could partial write. We'd either get it or we wouldn't. We write the value when it's allocated, at which point we've written into user acceptable memory and it gets overwritten with none.
Right.
Or we manage to overwrite the next pointer. And so as long as this is always attempting to race to overwrite that next pointer. So I think that's good. You want clean? No, clean's we're good with clean. So let's see if getting malloc and free in line makes this happy.
Wait, should we be receiving from R2? Shouldn't it be
Mm,
for printing it on?
down here? Yeah, I just changed that. I silently did it and then
No,
didn't comment.
Yeah,
You're
That's the
saying
last print.
where? Oh, that one should be. Yeah, yeah.
Yes, it's good.
Really?
Look.
This is where I just indent the whole thing and then say wild true. We are having some rotten luck there. Okay. So we are mallocing and freeing from 1. What are we getting there? Now that's a short value, isn't it?
Yeah.
Let's just sanity check ourselves here. That's a weird, it's a weird looking thing.
Well,
What's that?
that's a BSSN.
That's our PSS address. So my real problem here wasn't, or in this instance, what do I need to do? Let's just malloc again and print that bad boy. Like we're clearly getting the value in there, right? We finally saw a case where the address is getting there. And if the address can be in this malloc, then it's the next malloc that should have the secret value. We're not doing so hot on this race. I'm not sure what else I can. Why does this get grumpy?
It's just when I look at because out, right? Because then out is empty.
When we split, there's nothing for out.
Yeah.
How does that? Whatever. This is just really bad code. Where's my other receipt? That one doesn't need it. Just that first one. That means timeout is just not really putting in its work there, right?
Yeah. I don't know why but like why would it stop receiving early? It's really weird.
Yeah.
Because you asked for 10,000 bytes.
Okay. Malloc 1, free 1. Message is good. We get the space. Hmm. Because that means that we've written the value there in valid space, but that doesn't make sense. Because it should be one of these. You agree? Right? Like if it was in 2, then I should be overwriting the next pointer of 2, at which point it should be in 3.
So what's in 2 right now?
What's in 2 right now?
Right, since when we print F2 before we malloc 3, we had the our BSS address. So what's in 2 right now?
I don't have a good way. Oh, wait, we can just netcat to this, right? Fire up a new thread. We here should be able to print F. You want 2?
Yeah.
Like the same thing. Why is the pointer in both?
Because if we print F3 now, we see the COT. Oh, that's the same thing.
Well, those are both the COT thing, right? It's just not displaying the C.
Yeah.
Yeah, the non-printable character. So we're getting the same thing there twice. Let's see.
So you could look at the list of pointers, right? There's that array that's storing all of our allocations.
The array, yeah, we could look at that, but we just got that by printf 1, 2, 3.
Well, we know what their values are, but like, is it possible that the reason for this behavior is like 2 chunks are for some reason pointing to the same address? Like, I'm trying to understand like how is this even possible?
We could have done it to ourselves. What are we writing? Mangled target address. Mangled target address is the mangle of this. That's valid.
Oh, wait, is it possible that like that is still going on while we're doing those allocations? Because it's sending through R2. So it's possible that the program is still processing that like giant string of scanfs when we do the 2 mallocs, and then maybe it even overrides the like stored value. So we would want to make sure that those sends are done being processed before we malloc.
Oh, before this malloc?
Yeah,
Okay, so you want to
yeah, just like
wait.
for something.
All right, I'll buy that. Let's see if that works.
Although isn't that gonna wait for the fork process?
That's what I want.
I want to wait for the scanfs to be done.
For
Because I think
which,
that's what's happening is that the scanfs are still going on once we get to those mallocs, and then it's just
Good.
overriding the values there.
this wait
That's gonna wait for the
for this to be done.
yeah. We don't want that. We want to wait for the scanfs to be done.
No, the scanner, oh, they could be being processed and may have been sent.
Yeah,
Okay,
yeah.
all right, all right. Well, if that's the case, then we just send less.
Although it could, I don't know. Yeah. I don't know if there's a good way to tell if it's done. I guess you could send something. You could do like a printf from R2 and wait until you get the response back from it before you try and malloc stuff. One option.
You'd want to do what?
Like you could printf from R2 and then wait till you get a response from it outside of the for loop. And then that way we know once R2 is done processing things.
Okay, okay. So you want to send line printf1. You'd probably want to clean up here. And then receive until like message.
Yeah.
Okay. So we'd force it to output something. Wait for the output before doing the malloc. We're still getting our short value.
Right, but it's different.
I restarted.
Right, but it should be a
It's yeah, but yeah, you're right. But that's a BSS address, so that should be. Copy. Oh, we are consistent. All right. We have nailed that down. I just want to sanity check myself here. I did essentially the same thing that we've done so far. I'm not sure uh, where the miss is. It can be done. Of doing the same thing.
What's the other process doing? Why is it keep loading connections at these units?
Oh, I probably don't want that thing. I want this. Always a good sign when the code that worked doesn't work. Okay. Turn off one. Mount three, mount three. Good there. You can have more, but we're getting the same thing. I don't see it. That's going to guarantee. This is done on R2. I want the tcache that I'm corrupting is this one, which is in R1. So it is R1 that I want to malloc from. We may have to take the L on this one. Good thing we have 2 weeks.
Level one.
Well, the level 1 and whatever the last level of this is are remarkably similar, right? So like the difficulty curve for this module is level 1 and then like level 3, right? There's like small number things. That's why it's entitled primitives. If you take my garbage code and turn it into nice, pretty functions that kind of abstract away some of this, you can pretty quickly solve several of these challenges because the difference between, for instance, level 1, let's see, is this got the dojo here? The difference between level 1, which is read the BSS, and then level 2 is where the secret value is located. Right? And so it's going to place the value, for instance, on the heap or in the BSS or in the main process's heap in different regions of memory. And so if you've managed to abstract away arb_read into a function where it's arb_read some address, what this reduces down to is this nice little link right here, pivoting around memory. It turns out if you have a leak, for instance, in the heap, you can probably get to libc. And if you are in libc, you can probably get to somewhere else, for instance, the stack. And so level 1, yeah, it's got some pain, right? It's not the end of the world there. It's like right now we're trying to get to the binary, right? But since the binary was compiled without PIE, it's just this constant. So I don't really have to deal with this whole navigating different regions of memory. But the challenges progress by saying, hey, now it's in the BSS, except there is PIE. So instead of being able to hard code that memory address in the BSS, you'll have to reference this handy document. And I can probably always get a heap leak, right? And so how can I go from the heap to libc, and can I go from libc to the binary, right? It turns out in all of these regions of memory, there tends to be pointers from one region to another. And so the challenge of the actual module, aside from the pain that you just saw me deal with, is, okay, I can arbitrarily read something from the heap. How do I turn that into an arbitrary read of somewhere in libc, which is just I get a leak, I know where it is, I compute an offset to something else I'm interested in. So I get a leak into libc, I know hex 3000 bytes away is a pointer to somewhere in the binary, which I know an offset of 10,420 away is a pointer to the stack. All right. And so you're going to be pivoting around memory and hopefully doing that, writing a lot cleaner code than this mess, right? Because this is the same problem, just repeatedly done, right? I'm going to leak something from the heap, which then gets me to leak something from libc, which then gets me to leak something from somewhere else. And if I were to take this horrific mess and abstract it away correctly, that just becomes a small number of function calls of well-written functions that are handling all of these cases that I'm blowing up on, right? Like I could turn my leak thing. We saw sometimes I get an empty string. Sometimes I get an empty string. I could check for that in my code and just say, hey, if I got an empty string, go and try and run this race again, right? I could be a lot smarter about how I'm writing this. I'm purposely being kind of obtuse with it. Makes me a little sad that we didn't get the actual value, though. Because we are right there. See, now we're getting nothings. The tcache is saying underlying thread chunk. I think it's something with how we are. Let's print the that is mangled heap leak is demangled leak address. Leak address is in fact a number. So when we mangle that, we have a number. We can print the hex of the mangled target address. You could be getting that wrong. If we were getting that wrong, it would be because the mangled target, my mangle function is bad. Not demangle, where's mangle? Position bit shift by 12, XOR by the pointer, that is correct. We are mangling with the heap leak, which is the correct value. Marathon free one. Ah. Okay. That's interesting. We may be getting somewhere. I'm getting nothing because my heap leak is bad. All right, if my heap leak's bad, then I'm clearly mangling with nothing. That looks like something good. Look at this. But that has to be valid because if 2 was the pointer, I wouldn't be able to malloc twice.
Does demangling our target address give us FBSS?
Does
Just to say,
demangling?
check.
Okay. Here's my mangle. Right. Demangle of mangled target address. No, we probably want to hex that. Look, we're blowing up on 89. That's not a line to blow up on. There we go. Our heap leak. But you see how this is a bit of a mess trying to, there's all these fail cases.
That's not exactly.
That is not exact. I agree.
That's the problem.
That is probably a problem.
Well, the heap leak is also 1.
Well, that would also be a problem. I blame all of this on receive all. Okay, it all went downhill. Once we started getting fancy here with our receives. Because now we're blowing up there. And this is where writing better code that is reliable would make this way less pain. But if I do that, which I did 2 years ago, everyone just writes my code. My heap leak is 1. Why is my heap leak 1?
You might be able to see it's not working.
Let's just grab the next one. All right, we fail. Yeah, we're failing to get this heap leak now. It was perfectly good code. out split P receive times split. This was working. Yes. We were reliably getting a heap leak. Leak address. Let's print out. Am I just getting?
Just ones, yeah.
Now I just get ones. I don't know how we have managed to do that. We're going to malloc, we're going to free, we're going to do a ton of it. So we're losing this race now. F1 on R2, R2 receive. I think I have to throw in the towel, guys. But this is the exact kind of thing that wrapping up get heap leak into a function and then writing an assertion and checking it. It doesn't have to be an assertion, but some type of function where you're going to check your logic for these fail states, because some of these fail states are simply unavoidable due to the randomness of address randomization. I'm sure this is only a line or two away from actually spitting out the value that we want. But I'm not sure where the error is, and I think staring at it and randomly changing stuff is probably not the best use of time. And we have next week to run through this anyways. So I'll leave that there. Does anyone have any questions about like what was going on here, even if I didn't manage to spit out the value at the end? Yeah? All right, we'll call it there. I'll end the stream. Y'all are still welcome to hang out and poke me. I'll still look at this. I'm just not going to do it on stream. All right, goodbye, good luck. See you next week.